Yeah, okay,
So,
great.
yeah, thank you very much for attending, to coming to see and hear my talk. Today I will talk about the project that I worked on under supervision of Andrew Logsdale, and it was funded by the ECC project from ARCHER2. And its goal was to develop application programming interface API for the density functional theory software. I prepared my today's talk expecting that the audience is familiar with challenges of scientific computing, but not necessarily aware of challenges of particular molecular simulations. Therefore, I'll start from a short introduction to the contemporary landscape of molecular modeling. For those of you who are familiar with this matters, you can take a nap for a couple of minutes. Then I'll describe the API itself and will complete my talk with implementation details that I think should be of interest to everybody who works on development of scientific computing software, especially for high-performance computing software. So today there are generally, roughly speaking, two kinds of atomic scale models. The molecular mechanics models, also known as classical models or atomistic models. These models usually describe the system as a set of atomic nuclei, and they evaluate the dynamics of the system solely from positions of atomic nucleus and in terms of positions of an atomic nucleus. So generally, such models are described by a function of atomic coordinates. And for example, for water molecule, it's just a function of 9 coordinates, 3 for each atom. Another type of models, atom mechanics models, that is in fact a set of various approximations of Schrödinger equations that are called ab initio methods, or the first principle methods, wave function-based methods, or the workhorse of the modern computational chemistry and material science, the density functional theory. So the density functional theory and quantum mechanics models, I will use these terms as a synonyms. Few in this code is probably a rough approximation, but for the purpose of our talks, it doesn't matter. So the quantum mechanical models consider not just atomic coordinates, but also the electronic density around this nuclei. Therefore, for description of the same water molecule, you need not just coordinates of atoms, but also the wave function that could be described, for example, for water molecule with 440 coefficients. Apparently, it's much larger, and it scales. It also scales linearly, but the scaling multiplier is much larger. For example, for 100 molecules in classical models, you will need 300 variables, and for quantum models, you will need about 5 million non-zero coefficients. So applications of these kinds of models are the following. For molecular mechanics models, you can simulate huge systems such as viruses, proteins, or bulk materials. But usually such models are not very transferable, so one and the same model can be used for different systems. For example, in organics, they're usually limited by corresponding elements, and with bulk materials also you have to develop specific model for each material. On the other hand, the quantum mechanical models are much more flexible. They can describe the whole periodic system of elements, and also can describe interactions of materials with electromagnetic field that is crucial, for example, for solar cells. And for catalysis, it's crucial to be able to describe multiple elements, because it is interesting to investigate different metals for their catalytic activities. But of course, the high transferability of molecular mechanics models comes with a high computational cost, because even just the system, not talking about solving it, takes lots of computer memory. To address these challenges, currently there are two interesting approaches. Practical approach is the application employing of multi-scale approaches and, of course, machine learning approaches. How they work for DFT codes. In the multi-scale approach, usually with it you can join both molecular mechanics or classical models and quantum models for description of large systems, where you use classical models for surrounding large part of the system and quantum mechanical model for small subsystem of interest. In that case, you need to organize interoperability between two codes. One of them is a DFT code that will describe the internal quantum mechanical part of the system, and molecular mechanical code that describes the large part of the system. If you want to speed up your calculations with the density functional theory, then machine learning models can help you here. The core part of many DFT codes, of the most of DFT codes, is the Roothaan equation. That's essentially the approximate expression of density functional theory in matrix form. You can see this equation here. Essentially, it looks like a generalized eigen problem, but the problematic part here is the left-hand side matrix F depends on its own from the eigenvectors. Therefore, this equation have to be solved in self-consistent manner, and therefore initial guess over solution is desirable. It may reduce the amount of computational effort drastically. Therefore, there is a bunch of papers that develop machine learning models for that case, for that purpose. But there is a significant challenge with application of such models in practice, and it is due to scalability of of the data that you have to transfer between machine learning model, or the code that essentially implements this machine learning model, and DFT code. As you can see, for the same example, so 100 molecules, the size of matrices will be huge, and even if you apply a sparse representation, the size of matrices can be of order of tenths of hundreds of megabytes for not so large system. And that's if you want to conduct the computations fast, you have to transfer this data quickly. For QMMM interactions, the size probably could be not so easy to define, because it depends on the size of the system, but what you need to transfer is electrostatic and constraining potential that essentially a function in three-dimensional space, and the amount of data can vary from the size of your system, and also of course can be pretty significant. Therefore, we know that these interactions should be efficient, should be fast, and should be convenient to implement and to use. What do we currently have for these interactions? There is an interesting and widely adopted interface, socket-based interface API, but it is supports only classical quantities, so essentially atomic coordinates and velocities, and it can be used for example, for Roothaan matrices, for matrices of Roothaan equations. If you want to transfer the matrices over the Roothaan equations, you have to use file-based export or text-based export of these matrices. There are some tools that helps you with that, but it still needs the data conversion, synchronizations, and efficiently, and these problems are currently not solved. There is a few DFT codes, JPOV, Psi4, DFTK, that do have specific APIs, but only a few codes does that, and it would be nice to have more choice, have a wider choice for different purposes. So our own motivation of this project was stemmed from the larger project, development of multi-scale methods for catalysis supported by UKRI under supervision of Andrew Logsdale, and we particularly faced the challenges of data transfer between DFT and other codes while I was working on this project. So therefore, with the funding of ECSC, we have developed the atomic simulation interface API. We didn't think too much on the name and abbreviation, but we focused on the requirements to that code. So we needed that this API was efficient for large data structure, so it can quickly pass through the Roothaan matrices and electrostatic potential for systems of various sizes. It should be easy to use because we aim to develop complicated workflows with different FT codes and molecular mechanics codes. It should be easy to implement because we dare to think that these workflows will be adopted for different DFT codes. So it would be nice to see this API implemented in more and more DFT codes. Given that many DFT codes, modern DFT codes, has a long history and huge code base, we tried to design the API in such a way that so it could be implemented in at least as non-invasive as possible. So we don't want to introduce bugs in the DFT codes that implement the API. And of course, it should be portable. Therefore, it should be used with different languages like Python, Julia, C, Fortran, etc., etc. So, considering these requirements, we decided to implement ASI API as a plain C API because it can be implemented efficiently. C language is notoriously efficient, doesn't add too much abstraction penalty. Such API do not add complexity for deployment, so you don't need introduce dependencies from some external libraries. It is portable. Probably every language today has tools for interoperability with C libraries. It is compatible with crucial libraries of high-performance computing, such as API, BLAS, and BLUX. So, the key functionality supported by ASI API. It supports control flow functions. That's a minimal set. I will show them later. Functions for atomistic data transfer, that essentially coordinates of atoms, energy forces. It is not necessary because, for example, there is IPI interface for transfer of this data, but it wasn't too complicated to introduce, and it's essentially convenient to have all in one place. Of course, electrostatic potential functions for export and import of electrostatic potentials, for QMMM applications, and functions for transfer of Roothaan equation matrices for machine learning applications, for interactions with DFT codes with machine learning models. Overall number of functions approximately 24. Some of them can be used interchangeably, so it's approximate. So, Control flow functions. There are just 3 functions. First one is ASI init, that initializes the DFT library that is loaded in your script. The second one is ASI run, that essentially runs the DFT calculations. And the third one is ASI finalize, that actually closes freeze memory and closes the library. As you can see, it is really minimal set because we didn't want to introduce too many control points within existing codes that is usually implemented, designed to be launched as a standalone executable, not as a library. Therefore, there are no pre-designed borders between the initialization, running, and finalization stages. And also reinitialization is a purely tested case. So in principle, the library, it would be nice to have a library that could be reinitialized after finalization. But in practice, it is a purely tested case. Therefore, we do not declare that it is supported. The second set of ASI functions are atomistic functions. They essentially repeat the API functionality and provided for the sake of convenience. With this function, you can essentially place atomic nuclei in specific places, set the size of the cell, can extract the computed energy, forces, stress, tensor, and atomic charges, depending on the supported partitioning scheme. So, more interesting functions are electrostatic potential functions that can be used to extract external electrostatic potential from the part of the system that is computed with DFT, or vice versa, to import the electrostatic potential from the surrounding molecular modeling system, subsystem, into the DFT code, essentially. There are 2 actually to set electrostatic potential that is done within a self-consistent loop or during the self-consistent loop that is adopted from DFTB plus implementations. And essentially, once again, designed for QMMM embedding methods. As you can see, this to extract and to set the electrostatic potential, we use callbacks. We use callback functions. I will talk later about why we used callbacks. Just please note here. And the ASI API for Roothaan matrices. Currently, we do support import and export of the density matrix, that essentially the representation of eigenvectors for the Roothaan equations, the Hamiltonian matrix, and the overlap matrix. These matrices are only exported from the DFT code. We support polarization over key points and spin channels of these matrices. It also can be parallelized using blocks library, blocks API, and of course these matrices are these functions are mainly meant for QMML and machine learning interactions. So why? And in this case, for these matrices, we also use callback functions. So we essentially do not pass the matrices directly into the functions. We just register callbacks that will be invoked in proper moment within the DFT codes when these matrices will be calculated or will be required if you import or export, depending on if you import or export data. So why did we use the callbacks? First of all, because it's easy to implement. We didn't want to deal with copying of huge matrices from one process to another. It's much simpler to provide access to internal variables. Therefore, we avoid unnecessary data transfer. Also, in practice, we noticed that many DFT codes tend to reuse allocated memory, and therefore there, in some cases, there's just no such a moment when all three matrices exist in the memory. Therefore, you sometimes some codes, for example, as feature aims, just override the Hamiltonian matrix with the density matrix, and you essentially have to either have to make a copy in when you implement API, or we'll have to, as we decided to do, to pass the control flow to the calling code. So it may decide if it needs the copy of the Hamiltonian or it just needs some part of the Hamiltonian to do some computations. And of course, this approach do not disturb the control flow. You just, when you implement the API, you just can place the callback invocation in proper place and don't change your code significantly. Of course, the negative side of this approach is the inversion of control. The code that uses ASI API is not so straightforward anymore, but that's the cost of efficiency. So the general control flow of the client-side code, that is the code that uses ASI implementing DFT code, is the following. You load somewhere the ASI implementing library as a shared object, then invoke the ASI init functions, and after that you can repeatedly, depending on the particular workflow, there is nothing said about, there are no suggestions about this loop conditions. It depends on the workflow. It can be molecular dynamics simulation, it could be geometry relaxation, it could be enumeration of structures, etc., etc. So the general idea is you can set the geometry of your system, that is atomic coordinates, size of the unit cell. You can get information about the basis set size, so you can prepare the memory for your matrices if you need them. You can register callbacks for electrostatic potential that you import in the DFT code, and, for example, provide the machine learning density matrix to speed up the convergence. Also, you may register the callback for a Hamiltonian matrix that will be invoked when this Hamiltonian is evaluated within the DFT code, like in this case. So then you run essentially the DFT calculation. The long part happens here in ASI run, and within this ASI run, the Hamiltonian that is invoked or inside will be passed in your callback that you registered here with this function. And after that, when ASI run returns, you can invoke such simple functions as ASI energy, ASI forces, or ASI calc electrostatic potential. After the calculation, these things do not change, that they are saved already. So repeat it as many times as necessary, and after finalize, it is expected that the memory is freed and your DFT code is unloaded. So a few words about details of the implementation. Currently, we implemented the ASI API for two codes. Those are FHI AIMS and DFTB+. For FHI AIMS, we implemented ASI API natively, essentially introducing these functions in FHI AIMS code base. And for DFTB+, we added the thin wrapper that essentially reused some functions, some interface functions of DFTB+, but also, of course, we had to introduce some additional interface functions. It was convenient because of different pace of development. because our project is new and we need to develop it quicker. So also we have added the Python wrapper for ASI interface. It's called ASI for Pi, and it is meant to simplify usage of DFT codes from Python. So currently you can use ASI API from either C code, C client, or with a Python client via ASI for Pi wrapper. So ASI for Pi essentially implements two classes: ASI lib, it's for direct interactions via ASI interface, and ASI ACE calculator. It's actually a wrapper around ASI lib that simplifies setting up calculations. It actually reuses inside the FHI AIMS calculator and DFTB Plus calculator from the ASE framework. For interoperability between Python and C code, we used C types and NumPy C types libraries from Python. I'll tell about it a bit, a few of them. You can install ASI for Pi from pip repository actually. But of course you will need the ASI implementing code. It's either B plus or FHI AIMS. So what I want to add specifically about implementation of Python wrapper is that I've discovered for myself this nice pair of C types and NumPy C types libraries that greatly simplifies interoperability with C code. It's really simple. It's do not require compilation of some additional codes like CFFI that you probably know. You're probably familiar with. If your API is not huge, like in our case, just 24 functions, then the C types and NumPy C types provides a really simple way to wrap around the plain C API. It is efficient. It do not introduce unnecessary copying, and you're directly getting NumPy arrays that are wrap C arrays underneath. So here is a piece of code from ASI for Pi wrapper. As you can see, the wrapping of functions is really simple. Literally a couple of lines for each function. So you just describe the types of arguments and returned results. So just recommend it. So the the use cases that we expect will be for ASI API is once again electrostatic embedding, prediction of matrices from Roothaan equation, and different analysis of electronic structures such as charge partitioning, density matrix extrapolation in ab initio dynamics calculations, etc. Here is the minimal example of invocation of ASI implementing library, in this case DFTB Plus. You should link your code with the DFTB Plus shared object, and here is the simple code. You just initialize MPI, initialize the DFTB Plus with this ASI call, then ask DFTB Plus about the size of matrices. For example, if you need this for allocation of matrices in your code, then actually do calculations and getting the energy, for example. And of course, finalize your calculations. Here is a bit more elaborated example in Python. Here we use import of electrostatic potential from into the code. As you can see here is the piece of code that initialize the calculations, and you can see it works both with AIMS and DFTB. All the further code where you essentially register your electrostatic potential callback, run calculations, get energies, and calculate electrostatic potential from the DFT code. This code is actually the same for both implementation, for DFTB Plus or ASI. Therefore, we hope that the workflows that rely on the ASI API will be transferable between different codes. Here is a bit more complicated example with the density matrix import and export. That essentially simulates the machine learning workflow, where you have the density matrix predicted from the machine learning code, and you want to feed it in the ASI implemented DFT code. Once again, you just create the calculator with using both ASI and ACE framework. Here you can see that it's pretty short. And register callback in Python in this case. And once again, getting the potential energy and the density matrix from the DFT code. And you can use it. So ASI API currently is available in FHI AIMS code. It is in master branch, so just take the latest version and use it. DFTB Plus, it's still in development branch, but we hope it will be emerged in the master branch soon. The sources of ASI and ASI wrappers and tests are available on GitLab, as well as documentation, and the ASI 4Pi wrapper is available from PIP repository. So our future goals is to add support of sparsity of matrices. Currently it's not supported, partly because there is a huge zoo of sparsity formats in DFT codes. And the Hamiltonian matrices import, it's turned to be also available functionality. We thank our collaborators, Yu Yao, who is development of AIMS, Balian Taradi, who works on DFTB Plus, Thomas Kiel, Mariana Narus, Julia Westermeyer, that helped with prospective applications of ASI API. The project was supported by ECSC project. It's essentially the ECSC project supported by ARCHER2. It's part of FLF project from UKRI, and we also thank Supercomputing Wales for the provided computational facilities. Thank you. Thank you.
Great. Are there any questions? Feel free to leave them in the chat or just speak up, I guess.
Hello.
Hello.
Hello. So I suppose this is a question of different basis types for different codes. This is probably a problem that we've discussed together, but it's probably something worth enlightening other people about how you form interoperability between, say, plane wave codes and Gaussian type codes and codes that use different types of basis functions that are designed to give sparse matrix as formalizations through local functions.
So, do you see the presentation?
Yes, I do.
Okay, I just don't understand. So, essentially, the basis set is dependency is out of scope of ASI API. It is just works with matrices that are essentially the represents the coefficients of basis set expansion. And if your machine learning model, for example, was trained for a particular basis set, then it will work with this basis set. If you want to convert basis set, then you should solve it on your own on your own side when you extract these matrices from the DFT code. So in principle, there is no reason why it can't work with plane waves. In case of plane waves, you will have just you will not have this overlap matrix. It will be just unit matrix, identity matrix. If you have the sparse matrices, then implementing the API, you have to expand. Currently, you have to expand them in a in a dense format, because currently we expect that these matrices are in a dense format, but they can be distributed. You can see here that we expect the blocks descriptor and actually the pointer to the blocks data. This so currently we work with the ASI API expect blocks format for the matrices. So if internal representation of the matrix is different, then it's necessary to convert it. But yes, we are aware about that is the problem that we are going to address. So let's actually introduce support of sparse matrices.
Okay, thank you.
Mm-hmm. Thank you.
Any other questions? Okay, great. And in that case, I guess we should thank Pavel for a great talk. And I don't think there will be any more webinars until the new year. So thank you for attending all of these ones that we've had so far this year. And we look forward to seeing you again next year. Thanks.
Thank you.